And then another way would be another topology, input series, output parallel. Again, we allow the input to be double the voltage rating. For instance, if one transformer, we only have 110 volt. But if the input source is 220, then we don't have such power, such voltage rating. Then we can put these two in series. Then we're able to double the voltage rating. For instance, if you have a transformer used in the United States, the input usually 120. If you go to, say, Europe, then the voltage there will be usually 240. Then you can use two transformers, put them in series in the input side, then you won't have any damage to the transformer. Because you can see that later on, you can see that the power losses of the transformer highly relate to the voltage. So that's one of the things we can do that. And the output, we can parallel them up. We can therefore double the current. So by using this method, I can calculate the output voltage will be equal because the parallel input side, we're using a transformer conversion equation. You can see that the voltage conversion ratio becomes half of the turns ratio. So that's one of the way we can able to do that. Okay. So next thing to do will be we now putting two windings in series to each other. Series. So you can see the input and output voltage are both double. So in this case, you can see that because they are both double, now then we putting the input equation turns ratio, we can see that that will be equal to N2 over N1 again. But in this equation, we assume the input to each of the transformer in here, we are using half the voltage, half. So assuming this winding and this winding try to share the voltage equally, then we can able to get to this turn ratio. But in another issue will be, in case the two transformer is not identical, then we may not able to share the voltage exactly. Then, for instance, one is have a ratio, like 49%. This one, 1 minus 49. And then we put it together, we're still able to see the same turns ratio. That is to say, this kind of transformer is quite safe because we don't care too much about exact voltage conversion ratio. They can still able to balance, they can still able to produce a fixed turn ratio. We don't really need to worry about any internal circulating current. But you can see here, the voltage rating, if I show this will be double, output voltage rating also double. Current will be unchanged. Okay, so that's the phenomenon of the combined transformer. So in each case, you can actually build a new table to say how the voltage rating or current rating become varied. Some will be unchanged, some of them will double, right? But that's the way we're able to, using a basic transformer, but we can put in a few transformers together, and then we have a new rating of the transformer. Either you increase the voltage or current rating, either input or output side. So that's how we do that. So that's what we did last week. So next configuration will be if the conversion ratio between two transformers are not equal. Like in this case, we have one transformer 1 to 3, another transformer 1 to 2. Now then, I put an input in parallel, output in series. Obviously, can output 3 times V in because there's 3 here, and also choice of V in. Adding together, output becomes 5 times. So putting this transformer together, we're able to change the conversion ratio become 5. Okay, so that's one of the possible development. And then next thing to do will be, you see we have dot rotation here. We reverse the dot here. That means we are changing the polarity. Then it seems the voltage become subtraction instead of summation. Then this, we have conversion ratio equal to 1. So you can see that by using this method, two transformer, one is 1 to 3, 1 to 2, we are able to develop two types of the voltage conversion ratio, 5 and 1. So that's something quite special, right? Of course, you can see that input side, the voltage rating unchanged, output the current will be unchanged. So that means this current rating even though higher or lower, but we're still assuming two transformers have the same current. Okay, so that's why you can see that if you double check of the current rating, some transformer current rating will not be the same as before. So next scenario will be, if now I put it in such a way, this output side will be in parallel, right? Our input will be in series. So now output is the same voltage, V0, and then the input side is just using reverse conversion, the input become V0 times half. This will be V0 times 1/3. So in this case, then we are able to have this conversion ratio 6/5. Okay. So quite interesting. Now ratio becomes 6/5. We have another conversion ratio. And then if we reverse one of the polarity in one of the transformer, like in here, then that will, because it's just like dot rotation, right? Then we can change that into negative. So now then you can, this new conversion ratio becomes 6 instead. So we got a number of the possible. So now then you can see that originally two transformer, this configuration, we can able to have 5, and then we can have 1, five, 1, and then with 6, and 6/5, right? So two transformer able to have 4 different combinations, for a number of combination, we can have 4 type of the conversion ratio. Not only this one. Then we can, if we putting inside and outside input output, swap them by swap the input output with the transformer. It's really possible we can reverse this kind of the connection, right? Then that will become, after reversing input and output swap, then that will become 1. That will become 1/5, right? That will become 1/6. That will become 5/6, right? And then you can see the two transformer can get a number so many connection, possible connection. And also the transformer.
How we can change it?
No, you see, you got this box here. You have this box here, right? If now this input, this output, but now we flip them vertically. So now then, like in here. For instance, if now then change them into V in, this will be V out. Obviously, this ratio will be therefore become 5/6, right? We're just reversing, okay? Just like that. So
instead of 1:2, we are changing to 2:1, and
we just the whole thing. We are just swapping the input and output. Then we are just like a transformer. We swap the primary and secondary winding. Then we're able to reverse. You can therefore swap this one into 5/6, right? So that's why we are able to have 8 possible combination, of course not 8, because these two one are equal anyway. And the next thing to do, you see, we got original conversion ratio of 2 and 3, right? If you only see using single transformer, you got 2 and 3. And then if we put into, then we got 1. Okay. So that's why you can see that just this kind of connection, we can have so many 1, 2, 3, 4, 5, 6, 12 possible combination, actually become 11, right? So in theory, two transformer connection, we can have so many different combinations. Do you get my point, right? So that's also called the topology analysis. We like to stretch to use the topology analysis allow you to using simple transformer, but putting various connection you are able to generate a number of new voltage conversion ratio. So it's simple and easy to do the job. Do you get my point? But of course, in each of the case, the output current can be different from before because we are now putting two identical transformer in parallel series. So the current is not the original current. Like in here, 1/2, then the output current here compared to this output current, these two current are not equal anyway. If the two transformers same power rating, when we step up the transformer, the current will be stepped down. Yeah, so the current here, I out, equal to I in over 2, right? And this current here will equal I out equal to I in over 3, right? So, but of course, so in this case, you can see that the combination between them, but these two are connected in parallel. So the total contribution of current will be therefore equal to summation of these two, right? Because they're connected in parallel. So that means you need to have a very clear mind what will be the resultant current. Then another case will be if you look into this case. Now then, so the output current here, of course, equal to the input current over 3, right? And then this current, and then this current equal to output current equal to input current over 2 over 3. Okay. Of course, this I put on I dash here, right? So you can see that, but these two input current are these two, this one and this one, don't need to be equal, right? Okay, so that means if you want to examine the new output current, you need some calculation. They are not equal anyway. Doesn't like the previous case, they're exactly equal to each other. You get my point? Because they are connecting in series. When they connect in series, they must be equal current. But the transformer rating itself are originally different in current. So when this current are equal, then it reflect back to a primary side. The current draw in each transformer need to be recalculated to see how much current can go into each transformer.
V naught by V in equal to
V in are equal for both transformer, but the I in, this I in and this I in dash don't need to be equal. Can be anything. Because we just pair them up, we don't control any current. The current are controlled from the secondary side. So you can use this circuit to work out what happened to the I in for both transformer. I haven't done it yet. You can do it because that's one of the tutorial, one of the homework. The homework I'm asking you to redo all this for me and checking the current rating and power rating for each of the transformer. Do you get my point for the question?
yes.
Do you understand my question I'm asking? And maybe Sito, you can help me to describe the question again. What's my question here? And Ali, do you know what I'm talking about?
Yes, yes.
Okay, I start again. So this is for this transformer, right?
Yes.
Yeah. And this is only for this transformer. But now then, when you connect these two transformers in such a way, right? In parallel, right? This input current, this current are split into two current. One's I in, one's I in. dash. These two currents don't need to be equal. These two currents are controlled by output current after the turns ratio. Right?
So, whether you mean the output current will be the same.
The output current in this case will be the same. So you need to use the output current, the equal output current reflect back to the primary side
Yeah.
to work out the contribution from each of the input.
So, Professor, you mean like we have the input voltage, we have the set input voltage,
Yeah.
and because of the different conversion ratio,
Mm.
that voltage will be influence the second stage, and the second stage will have a current. This current will reflect to the input current.
Sort of. Yeah. So that means my requirement here for your homework will be now the output current are equal.
Yeah.
You can use output current to calculate back into the primary current for each transformer. Then you can know how this input current are shared between these two. How much current is this one? How much current for this and for this need to be calculated from this current. Okay. Yeah, that's our ratio. So you need to do that. Try to tell me the conversion ratio I already written down here. But next thing to do will be work out the current, how the current rating like for each case. The thing is, if you're thinking of my question would be if there are two different rating transformer, like for the two transformer, the power rating is fixed.
Yeah.
Then that may have some limitation for their due to the current become somehow we connect them in series. In here, this is in series. Then we're forcing these two current originally are not equal, but now are forcing them to be equal.
Professor,
Then that will affecting our total power rating. May not be originally double, maybe something else. Do you get my point? Yeah. Because you are forcing the two current, they originally not equal. If separately operate, of course, we have two power rating. But now we force the output to connect in series, then somehow we restricting output current. That means the power rating can be modified. So I'd like you to check for this phenomenon to tell me how the output power being modified. That's my question. So in this exercise is just to tell you about the combination of two transformers. We're able to provide a number of the output voltage possibility. In each case, they have their own current restriction due to how we connect them. So that will start up with one of the research thinking about when you adding different configuration together. Because the limitation of rating, parallel, series, you may have some new restriction. For instance, maybe only when you're working on a number of battery connect in parallel series, if one battery has limitation, the whole series battery will have the same kind of restriction. So this one the exercise to test what it's going to do. So your homework one will be have an example, ask you to do this. Okay. So do go home and think about that. You go 1.5 weeks to look into that. And then, of course, the question I'm asking is not only 1 to 2 or 1 to 3, probably will be 1 to 3 and 1 to 4, different kind of the turn ratio. Then you can check the whole picture, how the total voltage conversion combination you may have, and then how is the current rating for each case will look like. And then present to me. Yeah, okay. This in the homework you got a few simple numerical calculation. I think you can do it within half an hour. And then for this part, then you need to spend a bit of time to make sure you get the conversion ratio right, get all the combination to work out all the current ratio properly. Okay.
Is more 1 to
Sorry, say again.
is more 1 or 2?
You see the homework? Have you checked the homework?
One.
Yeah. I think homework I put down, I don't remember now, 1 to 3 and 1 to 4. Yeah.
More 1. In the one there are 6 questions or this one.
No, this one. No, this is another vessel. Another combination of the vessel. Question number 6.
6.
Question 6.
And then the last question.
Last question. Question 6. You see the question 6, then you can see my requirement, the combination. Very similar to this one, but you need to work out the current rating for each case and then comment to me. Yeah. Okay. Check that. You need some time to digest what it is. Okay. But at least you understand my requirement. The thing because you're all postgraduate PhD student, you should have capability to analyze various topology. We call it topology analysis, so that you are able to analyze the circuitry and generate a new combination and comment on each combination, advantage, disadvantage, and also the current rating, input, output. That's the basic configuration you should be able to fulfill. I mean, these do have a lot of the implication, because when you work on other transformer, this may be a transformer. This can be also DC-DC converter. If you say you have DC-DC converter like this, 1 to 2 double voltage, like 2 boost converter putting together, then how will the resultant voltage current rating? How will be the resultant current rating? The thing is, this kind of the configuration, you don't need to use current mode control. If this is a power converter, you can use current mode control to force the current contribution. But what I say here is naturally connect the 2 converter or 2 transformer. You naturally automatically can become this kind of the voltage summation or voltage subtraction, and automatically generate certain current configuration, input or output. It's naturally. You don't need to control. You're able to do it. So that's the thing I like you to do. But of course, this some of the exercise I like you to understand the topology development for circuitry. Okay. You get that? It's some time to look into that. That can have some future implication for other research topic. Next, we're going to look into an auto transformer. I think auto transformer, everybody has been using auto transformer. Basically, it's a transformer only a single winding. Usually transformer, we have double winding, output and input. So in this case, we have magnetic isolation. We call it galvanic isolation, which is able to have magnetic couple, no direct electrical connection. But somehow, if we want to reduce the costs, or we don't care about the isolation, then we can use single winding and put in a tap here, able to obtain any voltage by changing this tapping ratio. We're able to adjust output voltage. So that's quite something really commonly used. I think, for instance, in your experiment, you may like to buy this transformer to adjust the input voltage. For instance, many of my students, when they connect their power converter or their motor in 120 volt input, initially they scare about high voltage. So I told them to use this kind of auto transformer, start from low voltage, 10 volt, 20 volt, 30 volt, until the converter or machine is stable, more confident they can go to the full voltage. So that's commonly being used for auto transformer. Or auto transformer, in case you are changing the output power, then the voltage may fluctuate. But when you do experiment, you want to stabilize voltage. So you need to adjust this voltage slightly so that you're able to keep the output voltage unchanged. So that's one of the ways to do that. Of course, you can use power electronics to do the job, but when you do some simple experiment, you don't want to involve too much power electronics, then you can just use a winding transformer, auto transformer like this. So that's commonly being used anyway. So you can see that in here, there's a step-down version. So we got more winding on the primary side, less winding on the secondary side. It's just like a step-down transformer. But one thing you observe that will be this winding are shared between input and output. So we can see that before we check it in very detail, I may think if a winding is shared between input current and output current, it may have more current. But that's not the case, because by simple Kirchhoff's law, you can see that this current will be divided into this and that. So in theory, this current will be higher value than this one. So in a way, it's very possible that this current may not equal this one, can be higher, lower, whatever, but there will be some kind of current cancellation. We have less current in this winding. This is a step-down transformer. So that means output current will be higher than the input current. So if higher than this, the difference in here, so I2 usually higher than I1, so that's why I put on polarity here, I2 minus I1. And as you can see that this current will more look like going up in here. So this current will be at least lower somehow. So they don't, so that means to say, I can see that there's a current cancellation here due to Kirchhoff's law. We can reduce some of the current rating here. So that's the thing I observed that. And the next thing, I try to build up some equation to see how it looks like. Obviously, I'm using my convention here, V2 over V1 equal N2 over N1. I put down equal to 1 over N, yeah. Before I display, so I use N, right? 1 over N. So that means if the whole term is less than 1, is step down transformer. And then current rating, current conversion will be equal to N. Of course, I1, I2 are related by N ratio, like this, it's really very basic. More importantly, I want to check the current rating. This current rating, I2 minus I1 in this shared winding compared to input I1 winding. Why I need to do that? Because this is the same, usually auto transformer, we got the same copper wire to do the whole things. So if you do the whole thing, but if it happen to be this bottom winding has a less current impress them, then I may able to use less copper in here, save our money. So now that we have a configuration are inequality, so I2 minus I1, that means this current. If this amount is higher than input, why we do that? But input current usually will be less than I2 anyway. Once that subtraction, this comparison can be higher, can be lower. We don't know, we checking this condition. If that's the case, I build up the inequality, I find that N is greater than 2. N is greater than 2, or 1 over N is less than 0.5, right? So that's to say, I now build a relationship. For a certain amount of the N parameter, the current amount in this winding and this winding are different, can be higher or lower. But in this particular case, if this current amplitude is greater than this current amplitude, only when N is greater than 2. So that means when you design this kind of auto transformer, you can see that we are not going to use the same copper wire for the whole thing, because we know that we are able to have less current in here under certain conditions. Probably for this one, in this case, we will have less current for the design. As an engineer, we try to save as much money as possible. If you're going to manufacture 1 million transformer, if you see this configuration, then you're able to save some money for this copper, because due to cancellation of current, you can reduce the copper. So that's the issue I like to tell you. Of course, if your transformer are variable, have not to vary the tapping continuously, then you may need to use some wire that will be continuously vary in diameter to save some copper. Copper is very expensive. Usually when you buy copper wire, they measure by the weight per unit kilogram, rather than to measure by length or by whatever. Because copper wire more look like you're buying the copper mineral, right? So that's how we look into them. So this page is just tell you, we need to be careful. This current is not equal to this one. They are actually changing according to the N ratio. Next thing I like to examine about the step-up transformer, right in here. So that's to say, again, V2 over V1 equal N2 or N1 equal to 1 over N. So when this is greater than 1, then that would be a step-up transformer, right? If this greater than 1, that means N is less than 1 for step, right? Again, I want to build up the configuration. So now then, this current must be I1 must be greater than I2 because step up. So now then, the shared winding, if I1 minus I2, because I1 is greater than I2, so I put down I1 minus I2 for this amount of current. How that compare to the I2 current? So now then, if I try to work out the inequality, I1 minus I2, if it's greater than I2, what will happen to the n? Then now they end up with the n should be less than 0.5. So the n less than 0.5, we'll see that this current will be greater than output current. So that means in these two windings, for different value of the n, this current is different from this current anyway. So that's give us a design concept, how we design a transformer. Or in this case, a tapping transformer, or the tapping inductor. So the key message in these 2 pages will be, firstly, we found that for auto transformer, a simple transformer like this, then the current rating need to be especially designed. Don't waste the money in the copper because the top winding and the bottom winding have different current, mainly due to simple Kirchhoff's law. Many conventional design, they use the single copper wire diameter to do the whole thing. That could waste your money. And then your boss may tell you, you're wasting my copper. Copper is really expensive. You need to do this calculation to check what copper you're going to use. That's a property design. And then this will give you a simple phenomenon under what kind of turns ratio, what kind of current requirement for this. Very simple Kirchhoff's law, Ohm's law. Then you can observe this one. You see, when we conduct research, we don't need to use really complicated control method, blah, 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 measure to do that. Even those very simple equation like this simple inequality, you can able to observe this phenomenon. Then we can report that. We can do a good design. So that's how our engineers do. We know, although we are engineers, we're also scientists. Sometimes scientists will make the thing really complicated. But for practical engineer, we like to do something using simple equation to explain a phenomenon, and then we can get something to assist our design to reduce the design and also the manufacturing costs. That's the idea I want you to understand. All right, any question up to this point? So see how that can be some of the hints you think about your tapping inductor. Okay. So current rating is something important, not only the voltage conversion, but current is also important. Here will be a very simple tutorial to show us what's happening. Very simple. So we now have a step-up auto transformer. The turns ratio here will be N1 to N3, will be 2000 to 200. Input voltage is 2000. Output current rating is 500 M. Now we are asked to calculate output voltage and also current rating in primary side and secondary side. Current rating we usually using kVA, not using kW. Why is that? Because kW doesn't care about we care about the cosine angle, the phase angle. But cosine phase angle is not really right because sometimes a transformer can be any cosine angle, phase angle. So we need to use the maximum power rating is kVA, so-called the apparent power. So when you buy a transformer or a motor, we need to use kVA, not kilowatt. Kilowatt is not reliable. So now then ask you to calculate kVA, and then what's the current rating for the shared winding N1 here. We're more interested in that because the top winding here are defined by output current anyway. When you buy a transformer, they will tell you what is the output current. You know that. But they don't tell you this shared winding. That is the way we design as an engineer. We need to think carefully what that current is. So now then, let's look up the basic equation. VAB, AB here, over VBC, BC is just equal to M3 over M1. Yeah? Basic transformer. Then we put it into here, then work out the VAB actually equal to 200. So this potential is 200, this is equal to 2000. So this adding this one equal to output voltage. So output voltage equal to summation here equal to 2200. Very simple, straightforward, right? Very simple operation, everybody know. And the next thing is to get out the rating, kVA. Output side kVA will be equal to voltage multiplied by the current. So obviously you can see that 2200 multiplied by 500, you can get 1.1 MVA mega. Now being high power, we use not K, become mega, MVA, right? So output rating equal to this one. So you can see that I don't consider the power factor, because power factor can be anything, depend on output we connect to what kind of resistor or inductor. So kVA is the maximum apparent power. We use that. And then for the current, output current, I2 over input current, I1 equal to turns ratio. Again, then we can work out output input equal to output turn ratio. Then that would be N1 over N1 plus N3, right? Again, we work out the input current, in this case, would be 550. So you see output is 500, input here is 550, only different by 10% roughly. So we understood because this ratio roughly about different by about 10% anyway. So now then we use this, then the primary input side power rating will be 2000. Sorry. And then we multiply by this current 550. Then we got 1.1 MVA. Okay. So that gives us now the two ratings should be equal. For a good transformer design, input output power rating should be equal anyway. So that's fair enough. They both equal to 1.1 MVA. Then another more interesting point we look into will be the shaded winding. This one. So this shaded winding now be equal to again I in over I naught. I think we did that. This one. So we did that. Become 550 minus 500 become 50 amp. So the current here only 50 amp, much smaller than input and output, mainly due to the cancellation. So that means that now then, but the whole N2 winding is 500 amp, like in here. So you can see the current rating in the shaded winding are much lower. So this part of is 500 amp, but the common winding, shaded winding, would much lower. So you can see that we can actually reduce a lot of the copper from 500 amp. We can reduce 10 times to 50 amp. We can save a lot of copper in the shaded winding. So that's the message I give you. Many people decide, they randomly to decide, they use the same copper. They use 500 amp current copper. But in here, you can see that because the Kirchhoff's law, simple Kirchhoff's law, current cancellation, we're able to reduce the copper in here. This is a lot of the money. Okay. So this tutorial just show you the practical phenomenon, how we design tapping transformer, maybe tapping inductor. In this case, you can see how we need to understand the current rating. As an engineer, most important will be how we design, how to design the copper, so we can save money in this case. So this little section is not complicated, very simple, but has been ignored by many engineers or researchers, maybe my postgraduate student too. They just think, oh, transformer design tapping, same copper wire. But if they think about carefully, they see that there will be current cancellation. You can therefore use that's a proper method to design. All right? Any question? So that's why every time when we revisit some simple concept like transformer, tapping inductor, tapping transformer, you can see something special. We may forget to investigate in the past, but now then for this new topology, you can see, oh, I can actually understand better than before. All right? Good. So next thing is to look into the transformer. You see three-phase transformer, everybody knows three-phase transformer. I think you all know it, right? I'm not quite sure really yourself have to construct your own transformer in the past. You see many transformer document. You may observe many transformer. Have you really do your own winding for a three-phase transformer? Now I show you how to do that. For most of the power operation, then we tend to work on transformer when you more than 3 kVA, like in here. more than 3 kVA, then we'll use three-phase, mainly because of the power delivery. You see, when we operate on single phase, like in here, single phase, after rectify, then that will become this, right? If you want to convert to DC, like this, DC, then we need to fill up this area. That would be really difficult for single phase, such a big area. We need a big capacitor, a big inductor to fill up this gap. So that's why for anything three-phase, we prefer to, anything rectifier or AC to DC, we prefer to use three-phase in order to filter them. Much easier. If you look at the three-phase, like that, then you, after you rectify, then you can much easier to fill up this gap. This gap much smaller area for you to fill up. So that's why from one of the norm we are using for three-phase system, anything more than 3 kVA, we tend to use three-phase. Of course, you don't need to, but that's most of the industrial design to do the job. So now then, it shows you a number of the three-phase configuration. All the transformer, we can connect in Y or delta. For instance, in here, this Y, you can transform to delta. And this case will be delta to Y. Anybody can tell me why we need to use Y and delta? Why don't we just using YY or delta delta? Why we need to do delta Y or Y delta? What is the difference? I think you've done transformer in the past, briefly, right? Why we need to do that? Why the transformer like this? Y delta? Okay, what is that? Tell me.
Is that because like the function of like the dot in the transformer to perform that is up voltage or down voltage? For example, they say the delta is commonly used to set down, the delta Y commonly used to set up.
Not quite get to the point. I need to ask another one. Ali, what do you think? Why we need this kind of arrangement? Why delta, delta, Y? No? Who would like to comment on it? What do you think? You know, PhD, you should know how about
It is because in delta connection, the current becomes higher, and transformer is basically used to reduce the losses. So when it is from Y to delta, the current increases, and that's what we need at the end of the transformer.
Still not quite get to the point. No. You can see that in here.
So normally, like, what I think is like for this Y to delta, we know that in Y connection we have higher voltage, but in delta we have like V divided by square root of 3. So we are changing the voltage, like reducing it. If we want to higher up the voltage, then we use delta to Y. Like if we want to increase the voltage.
Yeah, close enough. You see, as you can see, each configuration here, in voltage, each of the, when we have Y connection, star connection, the voltage here will equal V over √3. We got less voltage. In here, this voltage equal to this voltage. You can see that for a transformer or maybe a motor. If we want to direct online, we will direct online. I'm not quite sure how about this direct. We apply 20 volt directly to a motor. Then the voltage during the motor is only stand still from 0 speed, you increase to full speed. Then in this case, the motor will be impressed with the full voltage. The current can be really large. I think you know that when a motor starts from 0 speed standstill, the transient current is really large, which can be have high pressure to the motor. But however, if we start it from star connection, we actually reduce the voltage impressed to each of winding by quite a good percentage, by this percentage. Then we have less start-up current. But once the motor has been accelerated to nearly the full speed, then we can using some switches to change the connection into delta. Then we can able to allow full voltage to the winding. So that's to say, we can able to reduce slightly about the start-up current initially using star. Then later on, we can change to delta. That's one of the phenomena. We are using the star delta start-up circuitry to do that. This kind of circuitry is just simple relay, simple switch. We can do that. So that could be quite useful when we're working with really high power motor system. When really high power motor system, some people don't like to spend too much money on the inverter. All these things we can use inverter to adjust the input voltage. But additional inverter can be expensive, can be a reliability. But if we just direct online, just connect motor to the AC, then we can use delta and star connection method. We're able to do it properly, right? So that's one of the way we are working on this kind of the connection. All right. So that's one of the configuration. So there's many possible connection, including delta to delta, right? And also star to star. So in 3V, you got 4 combinations because star and delta combination, 2 times 2, we have 4. And then for the actual form configuration, how we put the transformer together, like for Y-type star connection, we will have 1 winding, 2 winding, the 3rd winding here. So the magnetic flux from the A winding will go to the center, looping in such a loop. This one also looping here. This one looping here. Of course, for 3-phase operation, A, B, and C are all displayed by 120 degrees. So the free flux summation due to the vector sum will therefore equal to 0. So you can see that if they add up to 6, so the center limb here, we don't have any significant flux because the summation equals 0. So that's one of the advantage, one of the things we design transformer, we're able to have cancellation of flux in the central limb. So that's a wide connection. For this one, how do we connect the primary and secondary side transformer winding? Any recommendation? This only show you A, B, C. How about the primary and secondary? How are we going to do the winding? Where is the secondary side? You need to know that because you're double E engineer now, some basic thing. How do we put on the secondary side winding in this transformer?
This is a Y.
Why? Yeah.
So the second is the delta.
The secondary winding, how are we going to put on this magnetic core? How do we do the winding?
Series or parallel?
Huh?
Series or parallel?
Series parallel is how do we put the winding on that? Which location you put them? No matter series parallel. Huh? Put in center?
Center has not the flux.
No, you mean. So now if this is a primary, right? If this primary, then you need to put a secondary. Where do you put the secondary winding for A phase, B phase, and C phase? How are you going to put them? Where do you put why? Do you understand my question? This 3 winding only for primary. How about the secondary? Where do you put them?
Huh?
Stepping? What do you mean by stepping?
Taper, like tape,
Tape. We need to put some tape to isolate them to make sure they don't have any short circuit. Huh?
I think maybe the secondary should be, the core should be put on the same position.
On the center position? Yeah.
Because they have the same flux.
Put here?
No. The another side. We also have the 3 input primary. We also have the 3 output secondary.
Yeah, where's the output secondary? Like you saw
the same position of the input form.
the same position.
Yeah.
You mean here?
Share the same.
Here?
Yeah.
Yeah, that's correct. Yeah. The secondary winding we should also put on here. Secondary winding also put on here. Okay, the same. Of course, between the primary and secondary, you got some kind of the isolation tape to separate them in order to have better electrical insulation. They put in such a way. Yeah. Okay. We don't put in center because center have low flux, no coupling.
No flux.
We put them here more closely coupled to each other so they can better couple. We don't put on here. No, here we don't do that. We just put all together. Okay. And then after you do that, then you got this is primary, and then you got another secondary. How to put the winding in star and delta is your own connection. The transformer itself, they don't care. They only know you're putting 2 wire on the A and B and C, and then next you can connect them in different manner, become your star and delta. Okay. So a star and delta configuration all depend on how you connect them. The transformer itself, they don't care. They just put 2 primary and secondary in here. After that, you can just reconnect them into star or delta. Okay, you get that? So for instance, another type will be the E core. Okay, so come to see me tomorrow. And hello. We can have a weekly progress. Then you may come to see me tomorrow to discuss.
Yeah.
Tomorrow morning or lunchtime or afternoon also okay. Okay. So like this transformer E core, this is also popular. Then we also put 2 primary, secondary, primary, secondary, all putting together on the top of each other. Okay. So also have phase A, phase B, and phase C. Okay, that's the pedicle transformer. They are using E core to do that, but the previous one are using Y core. Okay, so that's one of the good configuration. We do that. Again, the A and B, we don't do that. These are not really good representation, but this showing them in the same kind of the limb, same limb, but actually so this is not on top of each other. They should one and then the other one and close them. Okay, so how we do that? Of course, these 3 flux, they are cancel out each other at this point. So that's quite okay. So we don't have any additional turn. If they are balanced, 3-phase balance, then these 2 add together will equal to 0 and will equal to 0. Okay, so that's the 2 major type of 3-phase transformer you see in many of the literature of pedicle circuitry, and how we do the winding. All right, any question up to this point? And then nowadays, we can consider how we can use 3 separate single-phase transformer become a 3-phase transformer. We can also do that because in many cases we found that we may not able to have single 3-phase. We can 3 separate transformer like this. So we can connect in such a way 3 separate. Then you can see that that's how we connect. In the primary side, we connect in the star connection. Do you see the star connection here? And output, we connect them in delta. This and this connect back to here, become delta. So become Y and delta connection using 3 separate transformer. So the thing is, we are able to provide more flexibility in this case. So that means we can using 3 transformer to do the job. And we can also, like in this case, we can connect in delta or star in our own feasibility. Because sometimes to source a single phase transformer will be cheaper anyway. So in this case, we can able to save a lot of the investment cost. And sometimes a three-phase high-power transformer will be also quite expensive. But using this method, we can actually have more flexibility. So that means my comment here, more flexibility. We can also use the modular design, many smaller single phase to do the job. Also, availability, we can easier to get a single phase transformer than three-phase transformer. Then also, we have more cost effective because in many cases, three-phase transformer and compared to single phase transformer, the cost will be quite different. Depend on the mass production. Sometimes you can get 3 separate single phase cheaper than 1 three-phase or vice versa. So once you have this flexibility, you can have some much better procurement, depend on the market at that time. Today, this market may be three-phase better than single phase, or tomorrow will be different. You got more flexibility. For the maintenance as well, sometimes you got 3 separate single phase, you can have a better replacement. You don't need to replace the whole three-phase transformer when it's being damaged. Then you can replace individual transformer. That can, in the maintenance, can be better. And also, balance and unbalanced overheating. You have 3 separate transformers. The heat distribution will be much better than single transformer. Single three-phase transformer, then you may, in a way, all the heat are being focused on the whole magnetic core. But now you separate into 3, and probably the distribution, heat management can be much better for you to reconfigure. Then somehow also efficiency. Somehow you can able to manipulate the efficiency calculation, 3 separate transformer and single three-phase transformer. The efficiency can also be much better regulated. And also for the voltage balancing, when 3 transformer putting there, you may have difficulty to balance really well. You can see that, for example, like in here, you see this A phase needs to travel slightly longer of the magnetic flux than the phase B. So in terms of balancing, probably they may not able to balance really well in some situation. But if you're using 3 transformer, your load transformer will be exactly the same. You can adjust each of transformer, match them properly to make sure these 3 phase are balanced really well. Even though in here, some of the winding may not able to balance really well. So that means this, you may have a select different combination of transformer. You can have different type of the new balancing. Of course, maintenance will be easier. The grounding can also become more flexible. You can create your own ground much easier than before. Okay, and by 45, we stop here. Then we continue next time to talk about the power losses. This is also a very simple equation, but we like to look into that, understand more about the power weighting and power losses. That's all. Any questions? Yes.
It's okay. I also don't understand why the difference of the Y and delta is because the Y is middle hasn't any magnetic flux, and what's the important point on this characteristic?
You mean Y and delta? How Y we sometimes use Y sometimes use delta.
So advantage of this group.
Actually, we can always talk about some advantage, disadvantage. But for three-phase configuration,
Yeah.
the basic topology for three-phase, you can connect them to Y or delta. That's a very basic layout. We can choose either one. So we're always using Y or using delta. But when we look into that, as I mentioned, when we start a transformer or start a three-phase motor circuitry, we can connect in either delta or star in order to manipulate of the current, low current or high current, or more voltage and less voltage. So one thing we can do. Another thing is, when we talk about the rectifier, that's getting more important. Because star and delta are different by 30 degrees naturally. Then you can check many literature, they're different by 30 degrees. So now then, if we connect the rectifier, like in here,
30 degree means
phase angle. So if you connect, so if there's a star, you have another delta in here. The phase angle of this and that are different by 30 degrees. So in a way, you can therefore have an even better rectifier connection. So that means when you put them all these rectifier together, so different of this can have a rather than 120, 160 become 30. Then if you use a multiple star delta connection, you have 30 degrees, and then carry on, you transform again. That's delta into star and delta. You can have an even other phase angle between them. So when you overlap them all, you can naturally have a really good DC come out. You not even need to use any LC filter. You can still able to produce really good DC rectifier naturally without too many of the L and C filter. We don't like use capacitor to filter because firstly investment cost, and also we just using too much energy storage. But using using the three-phase rectifier, I think you can check the website. We got 6 phase, 12 phase, and also 18 phase, 24 phase. This kind of rectifier, you're able to naturally produce really nice rectifier with really minimum amount of the capacitor being used, because they gradually reduce 30 degree, 18 degree, and so on gradually. You can check the literature. Really, there's a well-documented literature how to use higher phase of rectifier. So one of the advantage. So I guess there's a many discussion on this topic. Of course, in here, we don't focus too much on the transformer connection. But in here, we just introduce to you there with possibility we can use multi-phase transformer in order to reduce the ripple, improve the rectifier. Okay, any other questions? Good, then we stop here. Then we continue next week.
Mini profit.
Sorry, could you say again?
What is the mini profit?
Mini project. Let me see. I stop the recording. We don't